Chapter 7 was called Building Molecules, and we used this chapter to start to change our hypothesis yet again for what would allow us to best predict the smell of a molecule. We ended chapter 6 with saying and feeling pretty confident that the functional group was enough to sort a molecule into a given smell category, but we started chapter 7 by smelling a bunch of different alcohols. And what we said in chapter 6 was that alcohols would smell medicinal. And not only did none of the alcohols that we smelled in the beginning of chapter 7 smell medicinal, but they each had a different smell category. There were multiple smell categories that they fell into. So we, in chapter 6, introduced the idea of molecular formula and structural formula. In chapter 7, we went two steps further by introducing the ball and stick model and space filling model. Ball and stick model is an upgraded version of the structural formula. Essentially, it's a three-dimensional representation of a molecule using sticks to represent the bonds. Now, the space filling model is actually the most accurate because in real life there are not sticks holding atoms together. The stick is only a representation of a bond in this case. A chemical bond is nothing more than an overlap of the orbitals of two atoms where their valence electrons are. So space filling is more appropriate, more reflective of what a molecule would actually look like. Ball and stick model just tends to be easier to build, as we saw in class. We built a lot of models with the ball and stick model kits. Now, in a structural formula, Lewis dot structure, ball and stick, whatever model we're using, we can look at electron domains. An electron domain is nothing more than a region of space that electrons are occupying. And an electron domain could either be bonding electrons or lone pair electrons. And if it's bonding electrons, a single, double, and triple bond, they all count as one singular domain. Because a double bond, like between A and B here, even though there's two pairs of electrons, it's still occupying one region of space. This single bond is occupying another region of space. That lone pair is occupying another region of space. So a domain is just a region of space that electrons are occupying. And the way that those domains interact is the key to understanding what three-dimensional shape the molecule is going to assume. So electron domain theory says that all electron domains, because the electrons are negative, are going to repel from each other as far apart as possible and arrange themselves around a central atom to minimize the repulsive force that they feel from each other. And that really is the key to understanding why the molecules are going to have certain shapes they do. And the shapes that we went over were linear, bent, trigonal planar, trigonal pyramid, and tetrahedral. We started with tetrahedral, so I'm going to actually work from left to right here. Tetrahedral is where the central atom has four domains around it, but all bonded. So four bonding domains only. They will repel to be 109.5 degrees away from each other, arranging themselves in a tetrahedral. If we replace one of those atoms with a lone pair, I still have four domains, but now three of them are bonds and one of them is a lone pair. So 3 bonds, 1 lone pair is trigonal pyramidal. 2 bonds, and we should actually draw another lone pair in here. 2 bonds and 2 lone pairs, that would be like me replacing 2 of these atoms in the tetrahedral with lone pairs. I get a bent shape. And then if I replace 3, I just have linear. So a linear shape could form between just 2 atoms that are bonding, or I can have a central atom where there's 2 bonded domains and no lone pairs, and those 2 domains could get 180 degrees away from each other. Now, linear and bent look very similar. The difference is in a bent molecule, the central atom has at least 1 or 2 lone pairs on it that's going to push those terminal atoms, the outside atoms, downward in the bent shape, which is where the term bent comes from. The only other shape we looked at was trigonal planar. Trigonal planar is a molecule where the central atom has 3 bonded domains and no lone pairs. And this looks weird in terms of honk for us, but this is not necessarily representing a single bond. It could represent a single, double, or triple. It's just showing some sort of covalent bond between atom A and X. Trigonal planar molecule would be one in which the central atom, again, has 3 bonded domains, no lone pairs, so those atoms can get 120 degrees away from each other. So I gave you some other images there. right from our note packet that you can use to review those shapes. In larger molecules, we cannot say, like in this molecule, I cannot say that the entire thing is tetrahedral or bent or linear. There are several central atoms, nitrogen, carbon, carbon, and oxygen in this central atom, and each one is going to have its own shape around it. So the nitrogen here has 3 bonded domains, 1 lone pair, so that's going to be trigonal pyramidal, or trigonal pyramid, around the nitrogen. Around this carbon is going to be tetrahedral because of the 4 bonded domains. This carbon is going to be trigonal planar because of the 3 bonded domains and no lone pairs. And this oxygen is going to be bent because of the 2 bonded domains and 2 lone pairs. And what that allows us to do is get a better visual for what that molecule would really look like in 3D. It's not going to be flat like this where the bonds look like they're 90 degrees. It's going to be trigonal pyramid around the nitrogen and tetrahedral around the carbon, trigonal planar around this carbon, and bent around that oxygen. For much larger molecules, like the ones we smelled in the beginning of chapter 7, we would have way too many central atoms to go and list how many tetrahedrals we have and how many bents and trigonal pyramids and trigonal planars, and it wouldn't be useful for us. So we came up with some common terms to describe what the molecule looks like. And we had to use this mainly for alcohols and ketones for what we're going to review in a moment. But for these molecules here, we call them long and stringy because that's what they looked like. These molecules we called frying pan shape. Remember, these molecules had a ring of carbon atoms that was consecutive atoms bonded in a circular shape that was open. And then we have ball-shaped molecule, which is like we had a frying pan molecule, but then there were atoms that were bonding one end of the ring to another, so the molecule started to close in or bunch up on itself. And we said that the sweet-smelling molecules for alcohol and ketone functional groups tended to smell sweet. For alcohols and ketones that were frying pan shaped, they were minty smelling, and for alcohol and ketones that were ball shaped, they were camphor smelling, or they smelled like sort of like a pine tree. So the important thing here is that for many of the functional groups we ended chapter 6 with, it's good enough to use the functional group to sort the smell category, because for the majority of those molecules they will fit into one category. Carboxylic acids the majority of the time will be putrid. Esters the majority of the time will be sweet. But for alcohols and ketones, we have to go one step further and look at the shape. So if I identify an alcohol or ketone functional group, we have to go and look, is it long and stringy, in which it will be sweet? Is it frying pan, in which case it will be minty? Or is it ball shape, in which case it will be camphor smelling? And the very last thing we looked at was the receptor site theory. We introduced it at the end of chapter 7 and we built upon it in chapter 8, so we'll get back to it. But where we left off with in terms of how do we smell, we said the molecule needs to get into our nose. So that means the molecule has to already exist as a gas, or it's a solid and liquid that's turning into a gas. Because that molecule needs to break off of whatever the substance is and actually enter our nose, and the only substance that could travel into our nose, based on how the particles are moving, would be a gaseous substance. Once it gets into our nose, it's going to dock into a receptor site. It's going to make our way to our olfactory receptors and dock or attach to a receptor site based on the shape of the molecule. So it's sort of like a lock and key. The molecule will fit into a receptor and dock into a receptor that matches or most closely matches its own shape, tetrahedral, trigonal planar, or the larger shapes, stringy, ball shape, frying pan. Once it docks into a receptor site, it sends an electrical signal to our brain saying, hey, there's a molecule docking in this specific receptor site, or these several receptor sites are triggered off, so you should interpret the smell as sweet, or you should interpret the smell as putrid, or you should interpret the smell as minty, whatever the smell category is. But that is sort of a general overview of how the receptor site theory works. And again, we continue to build upon that in chapter 8. This brings us to the end of chapter 7, but we will continue this and wrap up our smell unit with a chapter 8 review video.